And for the general issue, we look at the every link layer, every link needs to deal with these general issues. And they are framing, which means that you need to delimit or signal the start and end of a frame. So the start and end of the frame will be clear, should be clear enough to the receiver. Okay, addressing. Okay, if it's point-to-point link, then it's trivial because there's only two stations on the link. At each end, there's only one station. So I'm sending a frame. The other side will receive it, and there's no addressing needed. However, in the broadcast link, you would need address specified to signal who should receive this packet or who this packet is destined for. Okay, so you need addressing. And so we call it the address we will use will be the MAC address here, which is the address, the hardware address of the interface card. And usually it's not configurable. When it's manufactured, it's hardwired on the interface card. So you can and you shouldn't modify the hardware address, which is called the MAC address, or called the medium access control address. Okay, the third issue will be the error control, and the fourth will be flow control. So these two issues happen again and again throughout the layers. We have seen error control in the physical layer. You can do the error control at the physical layer. And again, you may do error control at a link layer. And flow control the same. You do it here or you do it at the upper layer. And for error control, by the end-to-end argument, we know that putting error control in the link layer would not solve the problem ultimately. You still need to put it at the end-to-end, at the transport layer. However, in order to improve the efficiency in detecting and recovering errors, you put it in the link layer. Okay, so that's the reason why we see it in the link layer and sometimes in the physical layer too. Okay, so error control is about detecting or even recovering, correcting the errors. Flow control is to slow down the transmitter. You need to slow down the transmitter, or you need to synchronize the transmitter with the receiver so that the transmitter would not overwhelm the receiver. Okay, we want to make sure that the transmitter would not transmit too fast for the receiver. And then the final issue will be the medium access control. It means that multiple stations try to access the link, the broadcast link. Then you need to have a mechanism to resolve the contention. I mean, the multiple access, to decide who can transmit next. And if there are collisions, then what should be done in order to resolve the collision? So that's a MEC, medium access control. And it only appears in the broadcast link. Okay. For the point-to-point link, you don't need it because there's only two stations on the link, one at each end. Okay, one final comment is we at the link layer we call a data unit as a frame. However, in the network layer we call it packet, and then in the transport layer we call segment. So different term, but it means the same thing. But in order to differentiate whether you are talking about something in the link layer or network layer or the transport layer, we would name it differently, from frame to packet and then segment. Okay, so here we call it frame. And before we look at these issues, the concerns on these issues, we look at the popular links that have appeared in the history or are still active. Okay, so we put them into 4 categories. The 2 columns are personal area and local area networks, and the other column is metropolitan and wide area networks. And then at the 2 rows, you see the first row is on obsolete or fading away links. Okay, the links that used to exist or used to be popular, but later on they fade away. And the second row is on the mainstream, or they might not be mainstream but still active now. Okay. And we would not talk about the obsolete technologies. They are gone. They are history. And in the Appendix A, we talk about why some of the technology fail. So if you are interested in knowing why some of the important technologies failed, you can look at the Appendix A. I think there's a dedicated section on that. And in this chapter, we will talk about several mainstream links. The first one will be the point-to-point protocol, PPP, and then Ethernet. You will see Ethernet for local area network and also for metropolitan area, sometimes called last mile network, and also for the wide area, the backbone. So here Ethernet can be used for last mile and also for backbone. Right now it's popular in the backbone, but not as popular in the last mile. But it has a good chance to succeed in the last mile or the first mile. And it already succeeded in local area. And in fact, it dominates the wired segment, the wired local area. And then we'll talk about 3 wireless links. The first one is the wireless LAN 802.11, which is very popular now. And in fact, it grabbed a percentage of users from Ethernet. For example, right now I almost do not use Ethernet in my office. My office has Ethernet, but I seldom use the Ethernet. I use wireless LAN at home and also in my office. And it also, similar to Ethernet, it also evolved into different standards, different technologies. So it's getting faster and with much more bandwidth right now. And the other 2 wireless link will be Bluetooth. We'll talk about this, 802.15, and then WiMAX, 802.16. Okay. Bluetooth is popular. It grabbed a segment. It has a position in the market, but of course, not as popular as wireless LAN. But it got a stable percentage of market there. However, WiMAX 802.16 is competing with the LTE, another link standard. However, it seems that the operators, telecom operators have chosen to stamp on LTE. So if that really happened, I mean, if LTE is the chosen 4G technology, and WiMAX is a short-term technology, then it would signal the first incident that the Datacom camp loses ground to the Telecom camp, meaning in the past, say 20 or 30 years, the Telecom camp has competed with the Telecom. I mean, Telecom camp has competed with the Datacom camp many times, and over the past 20 years, the Datacom camp continued to win many battlefields. However, on 4G, probably this might be the first time ever that the Telecom camp has won, if that really happened. Okay. One evidence on the fact that the Telecom camp lost ground to the Datacom camp is Lucent, which was acquired by Alcatel, because Lucent invest much on the ATM technology and does not put that much emphasis on the IP technology. However, Alcatel put the same emphasis. I mean, they put the same emphasis on the telecom technology and also the Datacom technology. So it's kind of ensured that their investment, health of their investment is valid, and they survive. And eventually they have the strength to acquire Lucent technology. Okay. However, the LTE versus WiMAX is probably the first incident that the Telecom camp might win. Okay. So, however, we will talk about the WiMAX link layer here. Okay. So 3 wireless link and 1 wired link on Ethernet, and then 1 point-to-point link. So these are the things we will discuss in this chapter. There are some others, like for example, fiber channel, home RF or home plug for home networking, and DOCSIS for cable modem, which is still in good shape right now, and also DSL, ADSL, VDSL. They are they are having good market share. And SONET, resilient packet ring for special special purpose applications, and ATM still here, especially in the DSL technology, you will see some shadow of ATM. It's not the core technology, but it's part of the technology. But I believe that ATM will eventually disappear. And so it's a legacy technology that would take a while, would take many years to disappear. Okay, so let's talk about framing. The first issue for the link layer So you would need to let the transmitter need to some kind of signal somehow signal the receiver, the start of the frame, the end of the frame, and what fields, what attribute are in the frame. Okay, so you need the typical field in the frame format will be address length, the type of upper layer protocol. For example, if this is Ethernet, and what is inside my data payload? Is it an IP packet or something else? So I need to signal the receiver what's inside, what content, what payload I am carrying. I need to tell the receiver. So I need to specify the type of upper layer protocol. Okay, then the actual payload. Okay, that's the data I'm carrying. Okay, the data itself might be might start with IP header first, and then TCP header, and application header, and then application payload. But at the link layer, I don't care about what's inside. I mean, how many headers inside. I only care about what is the immediate upper layer protocol. So that's the type of upper layer protocol. And then at the end, you would have error detection code. And later on, you will see that most error detection code are put at the end or at the tail of a frame. Why it's put at the tail of a frame? That's because you will see that most of the error detection code are processed by hardware on the fly. So when you transmit the bit stream of a frame, you finish the transmission of a bit of a frame, and then you append the error detection code. So you are actually transmitting and doing calculation at the same time. And then after you finish the transmission of the frame data, then you append the error detection code. So that's why it's mostly put in at the tail of a frame. Okay. And basic unit of frame, how do you count a frame? I mean, count the units within the frame. You can count in byte or in bit. Okay. The Ethernet counts in byte, so it's called byte oriented. However, something like HDRC, they count in bit, then it's bit oriented. So the first thing will be in addition to the fields that you need to contain within a frame, you need to signal the start and end of a frame. That's called frame delimit. And frame delimit can be resolved in different ways. One is to put a special sentinel characters, or put a special bit pattern, or put a special coding in the physical layer. For the third method, you are relying on the physical layer to do the job. You don't do the job at the link layer. You ask the physical layer to do the job by special coding, or sometimes called invalid coding. So if you have a coding that is invalid in the data, it wouldn't happen in the data, and then that's invalid coding. And that can be used to signal the start and end of a frame. And other than that, you would have special character or special bit pattern to signal the start and end of the frame. And if you do that, you would need bit stuffing or byte stuffing to avoid ambiguity. The reason is because the pattern, the special character or special bit pattern you use might happen in the data. If it happens in the data, then it creates ambiguity to the receiver. So how do you resolve the ambiguity if the pattern, the bit pattern or character might happen in the data? You would use byte stuffing or bit stuffing. So here are two examples of byte stuffing and bit stuffing. So you have a frame. You send a frame, and then the end of a frame will be ETX, for example, ETX. So ETX is a special character. And what happened if it happened in the data? Then you would need to put another character before the ETX. So it's called byte stuffing. So when you transmit data and you see ETX within the payload, within the data payload, then you stuff DLE. The transmitter stuff DLE before ETX, so that it would destroy the pattern. And at the receiver, within the payload, if the receiver sees DLE, then it knows that this DLE, because this DLE would not be used by any data characters, shouldn't happen in the data character, then it would remove the DLE, okay, to recover the original pattern. If the receiver sees a DLE, if the receiver sees a ETX without seeing a DLE first, then it knows that's the end of the frame. If you are a receiver and you see ETX, and that ETX does not have a DLE in front of it, then you know it's the end of the frame. So that's called byte stuffing. How about bit stuffing? Okay, bit stuffing is a little bit tricky. It says that if the special bit pattern you use is 0 and then 6 consecutive ones and then 0. So that's 0 and 6, 1 and then 0. That's the start of the frame and the end of the frame, the bit pattern. And then as a transmitter, you transmit this. So the start of frame, you transmit this pattern. And then you start to transmit the data bit stream. And then if you see, it says that if you see 5 consecutive ones, then you stop a 0 here. A 0 here. Okay. You don't care what's next, whether the next bit pattern is 0 or 1. If it's 1, then it has a potential that the data has a special bit pattern inside the data. So immediately after seeing a 5 consecutive one, I put a 0 here. Okay. And here the same. If I see 5 consecutive one, and I put 0. Okay. So here these two cases differs. That this case has only 5 consecutive one, but this case has 6 consecutive one. But for either case, I stop a 0 after 5 consecutive one, and then transmit. At the receiver, if the receiver sees 5 consecutive one, and the next bit is 1, okay, so you got 6, 1, then it means it's the end of the frame. The receiver will know that it's the end of the frame. However, if it has been stuffed, then it will see 5 consecutive one, and then next one will be 0. So if next one is 0, I remove that one. So that's called destuffing. I destuff this bit 0. I destuff this bit 0 to recover the bit pattern. Okay. So there will be no confusion if the transmitter do it that way and the receiver do it that way. It's kind of mechanical. No error could happen. No misunderstanding could happen if you do that. If you start a 0 right after 5 consecutive one, and at a transmitter, at a receiver, you destuff the 0 after 5 consecutive ones. So it's kind of destroying the pattern within the payload. so that the receiver would, transmitter and receiver would not confuse each other. And Ethernet, you will see that Ethernet use the spatial bit pattern, to signal the start of a frame. However, it doesn't use this to signal the end of the frame. It uses a payload length to signal to let the receiver know how long the frame is, so that the receiver will know, okay, I know the start, okay, and the end will be in how many bytes, okay. So I don't need to worry about the end of the frame. So Ethernet does not use this or byte stuffing. Okay, next will be the addressing. In IEEE 802, they define a MAC address or the hardware address in 6 bytes. The first 3 bytes will be the organization unique identifier, okay, which is issued to the manufacturers. So a manufacturer might get one or several OUI, organization unique identifiers. And then the manufacturers of the interface card can generate the organization assigned portion, the remaining 3 bytes, so that for the manufacturer, it only needs to concern about these 3 bytes, whether I need to manufacture, each car I manufacture would have a unique 3 bytes. Okay. Then because the organization unique identifier is unique worldwide, and these 3 bytes at the end is also unique within the manufacturer, so the 6 bytes combined will be unique worldwide. So you shouldn't find an interface card having the 2 interface cards having the same MAC address. You shouldn't find you wouldn't find that. Okay, because they should be worldwide unique. Okay. However, there are indeed some interface cards that are manufactured for special purpose, that you can change the MAC address. But doing that is not good because it might, there's a chance that you in the same network there might be 2 cards having the same addresses. Then it will confuse the routers. Okay. And the first bit is reserved to signal whether this is an unicast address or multicast address. Okay. So now we have a 6 byte address. With each byte, there are 8 bits, and there's an order called transmission order, or sometimes called network order, or the host order, and each of them could be little endian or big endian. Okay. There is a sidebar. A common pitfall at the end of this chapter. A common pitfall at the end of this chapter describe little endian, big endian, network order, and host order, and the order could be in byte order or bit order. So there are 3 in 3 dimensions. little endian or big endian. And it could be network order or host order. And it could be bit order or byte order. So let me give an example because I'm not going to talk about this in this chapter, but you will need to read the common P4. So I have 6 bytes, and if my transmission bit order is little endian, and my transmission byte order is big endian, which is in IP. In IP layer, it says that the byte order, the network byte order, or the transmission byte order is big endian. Then, in what way are we going to transmit? If the network byte order is big endian, it means that you need to transmit the high order byte first. You transmit the high order byte first. And because the bit order is little endian, so you transmit the what? The low order bit first. Okay, so if I'm having a IP over Ethernet, and IP is big endian, byte order, and Ethernet is little endian, bit order, then what would happen? Then I would transmit in this way. I transmit from the high order byte first. But for each byte, I transmit the order bit first. Then I would transmit in this way, and then this way, and then this. So I'm transmitting in this kind of sequence. The bit sequence will be this. Okay, that's what happened in IP over Ethernet. You transmit the high order byte first, but within each byte, you transmit the low order bit first. Okay, that's the network order, bit order or byte order. And how about the host order? That's the order you transmit on the network. But how about you don't transmit, you store in the memory. When you store it in the memory, the 6 bytes in the memory, how are you going to store? In what order are you going to store? Here we don't talk about the bit order, we talk about only the byte order. And then if you have multiple bytes to store in the memory, and are you going to store the high order byte in the high order memory, or the low order byte in the high order memory? So I'm going to store, let me draw this. Are you going to store in the memory? Okay, and I have A plus 1, A plus 2, 5. Suppose I have 6 bytes. I can either store in this way, or I can store in the other way around. So that's another order. Okay, so if I'm storing in this fashion, the increasing order, then I'm the network, the host order, the host byte order is big endian. And if I'm descending the address, I mean the high order byte and low order byte, I'm descending the order, then it's little endian. And whether it's big endian or little endian depends on what? depends on the CPU architecture. Okay, if the CPU architecture is little endian, then it's still different in a reverse way as the big endian CPU. So it depends on the CPU. Okay, then that creates a problem. If I receive this 6-byte MAC address from the transmitter, and then I need to, first of all, I need to recognize the order correctly, right? Otherwise, I would misplace the high order byte as the low order byte. So first of all, I need to be clear what will be the network order in bit order and also in byte order. That's the first thing. And now we have explained that if it's IP over Ethernet, then I know the bit order is little endian, but the byte order is big endian. So I know how to interpret the bit stream correctly, right? Okay, and then after I receive it, I need to put it in my memory. Then I need to know whether my CPU architecture is a little endian or big endian, byte order in the memory. Okay, so I need to do that, put it correctly. However, if you, well, we don't want the programmer to worry about this. So what happened is that almost every operating system running on older CPU architecture, they provide a set of library functions, okay, that the programmer can call to transform the network to host order or host to network order. So you can transfer the order, and as long as the programmers call these functions, those library functions, then they'll be safe, and their program will be highly portable. Okay, so then you don't need to worry about the order as long as you call this transformation function, and usually those functions would have an abbreviation with N2H or H2N, network to host or host to network byte order. So as long as the programmer code this function, then the library function will be able to figure out, okay, the library function would need to read some configuration, okay, to see, okay, if this is Ethernet or if this is something else, and this is IP, so the order should be this, big endian or little endian. And also the library function also needs to read the CPU so that you would know whether this is big endian or little endian. So the library function would do the job to check the order and then do the transformation for you. Okay, and but however, it happens that the programmer does not or forget to put to call the library functions to do the necessary transformation. Okay, then something weird would happen, and those kind of weird things will be difficult to debug. Okay, perhaps you debug for a long time, and then you find out, okay, this is an byte order problem. Okay, so that's the big endian, little endian. And again, what I said could be found in the common P4 at the end of this chapter. Okay, next we will see error control at the link layer. There are two kinds of error control or error detection code used. However, the checksum and CRC. And the checksum is easy to compute by just adding up all words together and then transmit append the sum. So you transmit the data word, and then you add up, and when you transmit, you add up together, and then you at the end you also append the sum of your addition. Okay, that's checksum. And the receiver, it will receive the data frame, and at the end, and when it receives, it also do the addition, and then after finish receiving the frame, it would check whether the addition is the same as the end at the end of the frame, the checksum at the end of the frame. If my computation, my addition computation is the same as the checksum field, then the frame is correct. Okay, that's checksum. And CRC is a little bit more complicated, that it would generate a sequence by modulo 2 division. Okay, so you would append, it would transmit the data frame. At the end of the data frame, it would append the result of modulo 2 division. Okay, at the receiver, it will also do the division, and to check whether the division got 0 remainder. If the remainder is 0, then the frame is correct. If it's not, then it's in error. So let's take a look at the example here. That's CRC. So if you want to transmit the 11-bit here, the 11-bit, and you use a bit pattern, 6-bit pattern, and you would generate a frame check sequence, FCS, which is 5-bit. Then what would you do at the transmitter? At the transmitter, you do the division. That's 11-bit, and you append the 6-bit here, 6-bit of 0 here, and then you do the division. You take this 6-bit pattern, do the division, and then you get a remainder of 5-bit, a 5-bit remainder. And you take this 5-bit remainder as the frame check sequence to append into the end of the frame. So the transmitter transmits the 11-bit first, and when it transmits, it also do the division. So at the end of the frame, it would append the remainder here. So this is the actual bit pattern got transmitted, which was transmitted. So you transmit the bit pattern. That's the data, 11-bit. But now you transmit how many bits? 11 plus 5, so that's 16. So you transmit 16 bits. And then at the receiver, it would do the division again. And as you can imagine, because all these are ones complement addition, so you add this here, your division, or you do the ones complement addition, then you will get the remainder of what? 0, right? So you should get 0 here. If everything is correct, then this time you got 0. If it's 0 here, then you got this FCS. But if you append FCS, you do it again, you should get 0 here. So if it's 0, then it's correct. If it's not, then it's in error. So the receiver would only need to redo the division. And this CRC calculation is easy to implement in hardware by putting this, say for example, the 6-bit pattern here. So you would have 6-bit pattern input here into the exclusive OR. So you would have a sequence of exclusive OR logic gate, and each of these are exclusive OR. And then you have data frame input here. So that's 11 bits will be input here. You input here, and the 6-bit pattern will be the input here. So every time you do this, and it's equivalent to when you are doing a sequence. Well, actually, this is a sequence of every time it's a exclusive OR. So you do a sequence of exclusive OR operations, and you got a result. So it's easy to implement, and within just the 11 clock time. If the input is 11 bit, then within just 11 clock time, you would generate. Oh, sorry, not 11 clock time. 11 minus 6. That should be 5. No. Oh, sorry. 11 clock time. Yeah. 11 clock time, you would generate the result. Okay. So it's easy in hardware, but not as easy in software. In software, you do the division, and it will be a lot of instructions required. Many instructions required to do the job, but easier in hardware. So what happened is you got two choices, checksum and CRC. And further study shows us CRC is more sensitive or more robust to error. It can detect multiple bit errors. Okay. However, checksum can only detect single bit error. If you have multiple bit error, then say for example, if you have 2-bit error, meaning 1 becomes 0, 0 becomes 1, then your checksum result will be correct. 2 errors would give you correct result. Okay. So the checksum cannot detect multiple errors. However, CRC could detect multiple errors. So it's more robust to error. So that's the first thing. And CRC is easy to implement in hardware, but not easy in software. And checksum is easy in hardware or software. Okay. So the end result is that you will see that in the link layer, all the link layer protocol, they use CRC in order to get better robustness to error. And then when we would use checksum? Okay, we would use checksum when it's done in software. When your error detection is done in software, then you use checksum instead of CRC. Okay. So you will see that in the IP layer and TCP layer, UDP layer, they use checksum for error detection. They don't use CRC. But in the link layer, you use CRC, because in the link layer, most of the error control are done in hardware. But there's one exception. You will see that there's one exception, which is PPP. PPP is derived from HDLC, a point-to-point protocol. And when it was designed, they envisioned that this should be, the error control here in HDLC should be implemented in hardware. So they choose CRC as the checksum. I mean, it's as the error detection code. Okay, they use CRC. However, PPP implementation, when it's not shooting for high speed, high bandwidth, then it will be done in software. So you will see PPP implementation, almost all of them, all the PPP implementation are in software, in the driver. Okay, and the error detection there is CRC, but done in software in the driver. So there are indeed some exception. You do CRC, but in software in the driver. However, on Ethernet, on wireless LAN, on something else, some other links, they all use CRC, and it's done in hardware. Okay. And then you would ask why we use, since checksum is not that good, not that robust to errors, then why are we still using checksum? Okay. In IP layer, in transport layer, why are we still using checksum? We use checksum only for the IP layer and the link layer and the transport layer. We use checksum mainly to detect the nodal errors, or namely mostly the memory error, sometimes in the protocol processing error. So it's additional check or double check. So for that kind of double check, we would use a simpler mechanism. In the meantime, the IPv6, in chapter 4, you will see that in IPv4, we have a checksum in the IP header. But that checksum field has been removed in IPv6. In IPv6 header, there's no checksum. So that double check is skipped. In IPv6, it doesn't check. Okay, and you would say, what's the reason? Because we later realize the chance for nodal error is small, and spending so much time doing the checksum calculation at routers might not justify, because the nodal error rate is low. Okay, so it removed the checksum in IPv6 header.